So, when we talk about crypto asset sustainability, a key question that we need to ask is how do we measure that? And secondly, what are we even measuring? Because sustainability by itself is a really broad term and it can talk about a lot of different things. When we talk about crypto asset sustainability, one of the first things we typically look at, and one thing that we see a lot of headlines about, is the energy consumption of the Bitcoin network. There are two main sources for that, so you can find live data about the energy consumption of the Bitcoin network on either my own website, the Bitcoin Energy Consumption Index, or you can find it through the Cambridge Bitcoin Electricity Consumption Index. Both have different methods, and I don't want to tire you too much by the technical details of those methods, but I do want to point out that if you look at these two different approaches, if you take the total numbers over last year, per my own energy index, Bitcoin was consuming 134 terawatt hours of electrical energy, and per Cambridge, that number was 104 terawatt hours of electrical energy. So I think ultimately the difference between the two methods isn't that interesting. I think the key thing is if we're looking at the energy consumption of the Bitcoin network nowadays, we got a pretty good idea about those numbers, and we can use those. But then the question is, okay, and what then? Because that's just Bitcoin. There are more assets like Bitcoin out there. The biggest one, the second biggest one that's using proof of work mining like Bitcoin is Ethereum at the moment still. They haven't completed their switch to proof of stake yet. And after that, you have crypto assets like Dogecoin, Litecoin. They significantly consume less energy, but at the same time, it also scales along with their market capitalization, because ultimately what we see in a lot of these assets is that their energy use is just related to how much the miners are earning. So simply said, the miners, if in these systems, if the value of the asset is zero, they're going to be making $0, and they're not going to be able to pay for the electricity bills. So the higher the asset value, the more electricity and the more hardware they can afford. This is a bit of an exclusive image, so I did the calculation based on my own energy index approach and the Cambridge approach for the top 10 largest crypto assets that are making use of proof of work mining. Note that the site is a logarithmic scale, so otherwise the smallest one wouldn't even be visible. But with this image, I wanted to show that if you're applying this approach, the ultimate result is that you can conclude it doesn't really matter which proof of work asset you take. They're all equally impactful. The market capitalization moves exactly in line with their percentage of the respective power demand. But then what? We got an energy consumption estimate. We can do it pretty easily. But in order to give that some meaning, we need to know where's that energy being sourced from? What is ultimately the carbon emissions related to the energy that's being used? That's a tough question. Because mining is somewhere you can do anywhere in the world, and we don't know which miners are located where. Now, the good news is Cambridge provides us with a lot of data about where miners may be located, and they seem to be doing quite a good job at providing those locations. So we can use that to evaluate, okay, if this is where miners are located, what does that then mean for the power that they're using? And if we look at that, we see that historically there's been a lot of fluctuation in the power sources of the network. A key reason for that is that up until last year, a lot of these miners were located in China. And within China, they were moving around. They were moving from the north of China in the wintertime, the dry season, to the south during the summertime and during the rainy season, so they could take advantage of cheap hydropower and then migrate back to the north and use coal during the winter months. And it's nice to see that that migrational pattern just shows up when you look at the data over time. We can see the summer periods with a lot of hydropower. We can see the winter months with a lot of coal-based power. But then last year, and I addressed this earlier today, China said we had enough. They found that these miners were responsible for the revival of some idle coal mines, and they just didn't want this crypto mining industry anymore. They wanted to comply with their climate targets, and they just kicked out this industry. The ultimate result of that was that a lot of these miners migrated to countries like Kazakhstan and the US. And the interesting thing there is that even though we don't perceive China as a very clean country, the Bitcoin miners over there were doing quite well because they were getting a relatively high amount of higher power. But when they were forced out and they had to migrate to the US, they now got into a situation where the grids are more reliant on coal and natural gas, especially in the US. The primary energy source is natural gas. So what we see is that the average electricity mix is also changing. The majority of the network was already powered by fossil fuels, and that majority increased, mainly due to hydropower being traded in for natural gas. And another issue is that even though we see the share of coal going down, you would think, okay, that's great. But unfortunately, the Kazakhstan coal is probably one of the worst sources of coal in the entire world. Because in Kazakhstan, they primarily rely on hard coal, which is the worst type of coal you can be using, and they have a really inefficient way of processing it. So ultimately, the carbon emissions of that can be 50% higher than what would be normal in the US or in China. Altogether, that means that also the carbon intensity of the network has been increasing for the Bitcoin network over the past year. And ultimately, this means that the entire network has a carbon footprint of, we estimated, 65 megatons of carbon dioxide per year. This was a couple of months ago, by the way, so in the meanwhile, the energy use of the network has been going up. But this data is based on August last year. And back then, this is the quantified footprint. What does that mean? Well, 65 megatons of carbon dioxide, it's more than what a country like Greece is responsible for every year. It's also more than what we're saving from deploying electric vehicles around the world. So we're talking a pretty substantial number here. It's around 0.2% of our global carbon emissions. And of course you can say, okay, well, there are bigger things, but it's definitely not an insignificant amount. And the interesting thing about this map is it also shows where those emissions are being sourced from. So we see, like I just said, Kazakhstan and the US are really driving this number. And also within the US, we see that states like Texas, Georgia, Kentucky are key drivers for carbon emissions of Bitcoin miners in the US. And that's all because of the reliance of natural gas and coal within these grids. One of the reasons why Bitcoin mining is so popular in these states, I think it's good to point out that Kentucky last year introduced tax breaks to lure these miners to their grid. And they literally said, you know, we have an obsolete coal industry and we kind of like to have a buyer for that. And Georgia is actually moving in a similar direction. They are also recently talking about introducing tax breaks for miners. And Texas has been very welcoming to these Bitcoin miners as well. I think the governor said, okay, this is going to fix our grid. Well, like I said at the beginning, when we talk about sustainability, we also need to talk about those kind of things. So we can't just talk about the energy use and carbon emissions. We also need to talk about things like, hey, the system is using highly specialized equipment. If you're mining Bitcoin, you can't just do that with any laptop. You need a very professional mining device. And you're going to need a lot of chips to create that machine in the first place. We're already dealing with a global chip shortage. So we're going to be using some capacity that we could also use to do other things. I can't quantify the impact of it. Just want to point out that we're in a global chip shortage. So if we're putting chips into highly specialized machines that can't do anything else but mining, we lose capacity for other things. And the other thing is that these machines tend to become obsolete pretty quickly. The only thing they can do is mining, and they are in use for as long as they are profitable at their task. So while they're making money, that's great, they're running. But typically in a period of 1.5 years, they get to their break-even point. And then the question is, okay, what are you going to do with your device? Are you going to store it, hope that the Bitcoin price go up? Or the only alternative is throwing it away because you can't repurpose the device. They're using highly specialized chips. So also the e-waste output of this network can ultimately be as high as, well, my home country, the Netherlands, at least in terms of small IT equipment, which is an additional issue on top of the energy use. It just comes on top of it. The energy use is not just emissions. It also means that in a lot of cases, these miners can overload a local grid. We have seen that in so many cases by now that all these miners are looking for cheap energy, cheap electricity. They all want to get the same cheap sources because they all have the same biggest expense, but it's driving them to the same locations and it's overloading those grids. So that's why we see on the right side numerous examples of grids that have been facing, in the worst case, power outages as a result of all these Bitcoin miners coming to their grid. And it's a big issue because ultimately, if people are left in the dark, you're not left in the dark when everything's fine. You're left in the dark when there is a peak in demand, which happens if either it's 40 to 50 degrees outside or minus 20. So this can actually put lives at stake as well. And this is just, again, on top of all the other things. It's all the things that we need to consider when we talk about crypto asset sustainability. Now, the good news is, I've been talking a lot about Bitcoin and its proof of work algorithm, but there are other solutions to running a crypto asset nowadays. So Bitcoin isn't entirely representative for what's really going on in the space. In fact, I would expect that most projects nowadays, and especially the new ones that are being launched, they don't use proof of work to bootstrap anymore. They will typically run on proof of stake or something else. And the nice thing about proof of stake compared to proof of work is that whereas in proof of work, you have this really massive lottery going on with all these devices just constantly running, trying to guess a winning number and hoping to guess one right so they can get to create the next block for the blockchain and get a reward for that. In proof of stake, you don't need that. The only thing is, what you need to do is, you need to get some coins, you need to put them up as collateral, and the protocol will randomly assign the right to create the next block to the blockchain to one of the people who put their money at stake. What you need is coins and a device with an internet connection. You don't need to have your machines running 24/7, and the amount of machinery you have running will not change your odds of winning. So the nice thing about that is that it takes away the hardware-based competition, and it can tremendously reduce the amount of energy we require to run this type of systems. I wrote at the top here that if Ethereum succeeds in changing its algorithm from proof of work to proof of stake, which is what they're working on, they could save up to 99.99% of their energy consumption, which is a pretty massive amount. It's just 1/10,000th of what they're currently requiring. But it's a very difficult thing to estimate still. Ultimately, we don't know how Ethereum will really look like once it switches to proof of stake. How many nodes will be active in the network, what will be the hardware requirements, how will that develop over time, because as the network grows, the hardware requirements might also grow, and the energy consumption might grow, unless Ethereum also manages to implement sharding. It's a very fun discussion you can have on that, but there's just a lot of unknowns to such a prediction. And moreover, we still see a lot of differences even within the crypto assets that are based on proof of stake. So at the bottom here, I got a report from the Crypto Carbon Ratings Institute that was published several weeks ago, and they looked into, okay, how much energy do these proof of stake based blockchains really require? And they took a hardware-based approach, so they just checked, okay, what do we need to really be able to run a node in these networks, and then used those hardware requirements to come up with an energy estimate for these networks. And what you see is that if you look at this metric, the electricity used per transaction, you can see that some systems are a lot more efficient than others. It ranges from 50 watt hours per transaction to less than 1 watt hour per transaction. Now, just to give this a little bit of a meaning, if we would look at the energy use of a payment provider like Visa, the energy consumption per transaction would be around 1.5 watt hour. So some of these are doing really well, but if you look at Cardano, they're doing almost 30 times that. So you could be wondering, hey, if we're switching from our current system to Cardano in this case, we would be increasing our total energy use by 30 times, which would still be pretty bad if you think about it, because ultimately it's a significant factor. It's just that with proof of work being around, it tends to take away the focus from that, because it adds such a large amount on top of that that we forget that proof of stake by itself isn't always perfect either. And I think this was one of the points that was raised during an earlier talk. If we move to proof of stake, we're not necessarily there. This is the last bit. And it's difficult to solve, because ultimately this is blockchain. Blockchain relies by design on the replication of data, replication of processes. If we're doing things in a single server, if we're moving that stuff to a blockchain, what happens is we're going to need multiple servers. And I don't know how many there are ultimately going to be, but it's going to be more than if we just take that single server. And there can be a benefit from not having to rely on that single server, because that's also blockchain. It takes away the centralized single point of failure, but at the same time, adding that trust through distributing data comes at a price, which is typically a reduction in efficiency. So we always have to think about, does our use case really warrant that we put stuff on a blockchain, or should we be, are we fine with our current system? Do we trust the people that we have? Because trust actually tends to be more efficient than whatever we can do on a blockchain, unfortunately. But again, I just want to stress that doesn't mean there's no good blockchain use cases. It just means that we have to be really careful in considering our options here. I haven't said anything about Filecoin. I have one minute left. I would assume that Filecoin is probably somewhere between this type of proof of stake networks and ultimately proof of work networks, because there is an incentive to employ solid state drives, but the energy consumption of that is going to be less. So the ratio hardware to energy is going to be very different from what we see in Bitcoin, probably low on energy and relatively high on the hardware. We only just have seen the first steps to evaluate the energy consumption of a proof of storage-based network, and I think it would be a next step to also look at what can we measure in terms of electronic waste output ultimately, because that's also part of the questions that we need to ask. I think I have 30 seconds left, so I shouldn't add any more points. I'll just keep it at that. Maybe one question.
Thank you. On the previous slide, the watt hour per transaction, is that calculating also all the validators, all the set, or the single node that validated the transaction?
What we typically do is we take the total energy consumption of the system, and then we divide it by the number of transactions that's being executed in total. So okay. Everything added up together. For Bitcoin, these numbers are a lot higher. Then we're not talking about watt hours, but we're talking about kilowatt hours. A single Bitcoin transaction, well, if you look at my data today, it will say it's equivalent to 2,200 kilowatt hours of electrical energy consumption, and per Bitcoin transaction also a carbon footprint of more than 1,000 kilograms. Might be hard to wrap your head around that, but that's more than a per passenger carbon footprint of a flight from Austin to Amsterdam.
Yeah. Just ever so quickly, a related question. When you're calculating the carbon emissions for each of these networks, what type of emissions factors are you using?
Sorry,
The emissions factors, are you using generalized, annualized emissions factors for each country where there are node operators? Or are you using something more granular, such as like based on the locality of where those operations are taking place?
This is just based on averages. So indeed, we take the location and we just apply the average emission factor of a grid. You could actually argue that if you're going to look into this, one thing you should be doing is you should look in the marginal impact, because ultimately when you increase the demand on a grid, what's going to happen is some type of fossil fuel source is going to come online to power that. The marginal resources in most cases, especially in the US, is coal. So any increase in demand is typically going to be sourced from coal. Unfortunately, we can't really specify that properly, so that's why we had to go with averages. But even on averages, Bitcoin got less green over the last year. So if we would look at the marginal impact, the numbers would probably be even worse.
Worse.
Yes, a lot.
For Bitcoin
Because
specifically, they would be worse over the past year. But if you're looking at some of these networks, such as, say, Polkadot, that's the nodes are predominantly run in Europe, the marginal emissions factor for those grids is potentially much lower than here in the US.
It depends. I mean, in Germany, the marginal resource is still coal, so it really depends on where you're located in Europe. I think in most cases, the marginal resource is fossil fuel. The marginal emission factor is going to be higher than the average. There are exceptions, of course. You would have to check. That's difficult.